You can see, I hope so. It's a bit shaky, but anyway, let's start the lecture. Assalamu alaikum once again. This is the last lecture of this week. We're looking at complex numbers. Sorry, the last video just ended abruptly, but anyway, 6 minutes, okay, then I add on to this. So just to show you, it ended here. I was explaining about multiplication. So now I want to just give a general recap of what happened last time. And basically, we started to talk about complex numbers. Section 17.1, that's our aim. Talk about complex numbers, and specifically, just to remind you that anyway, that it's just a set that has two aspects. It has a real part and imaginary part. This we call algebraic form, or you can think of it geometrically as coordinates in that space. So you'll have the horizontal axis, which will be the real axis, and the vertical axis, which will be the imaginary axis, which will be y, and the x coordinates for the horizontal axis. So you have the real part, x, the imaginary part, y. Then we denote a set of complex numbers by c. This is the algebraic form. Remember, our I is the same as the square root of -1, or I squared is -1. The real number is a subset of the complex numbers. I think I explained that. And then we also said when the two numbers are equal, complex numbers. Now, this whole thing just summarizes what field is, okay? The rational numbers, real numbers, those are fields. Now, when you are doing modular arithmetic, you looked at Zn, 0, 1, and so on. Remainder on division by a number. If you take that set, integers and then positive integers, remainder on division by a prime number, you get a finite field. Anyway, so what's a field really? The set of complex numbers happens to be a field, a set in which you can perform the four basic operations of addition, subtraction, multiplication, and division, and commutative law, order for any two numbers, doesn't matter when you are adding or multiplying, and order for any three numbers when you are multiplying, adding or multiplying, which is called associative law, holds, and the distributive law holds. So anyway, a quick recap of this and then where we were is that 0 is there. When x and y are 0, then you have 0. Then addition, we just said you just pick z1 and z2. Just pick the real part, add to the real part, the imaginary part, add to the imaginary part. Finish. Subtraction, you do the same thing. Multiplication, well, all I should just tell you is that you just multiply the way you used to do expand binomial expansion. So this times this, plus this times this, plus, I don't know, this times that, plus this times that. You end up with this. The only part here is iy1 times iy2 is I squared, y1, y2, but I squared is -1, so this is why this is minus, like that. Finish, halas. Then division. Now, division of complex numbers, probably I should jump this for the future, but anyway, maybe let me see whether I can do that. We are teaching something and then you jump to something else. When you are, okay, so let me just explain to you briefly, but I'll go back there. When you're dividing two numbers, so the next step would be, you multiply this fraction by the complex conjugate of z2. Well, complex conjugate, this z, real number, no, complex number, then its complex conjugate is by z, which you just negate this part. So, now, so the multiplication of z1 over z2, or rather division, will just be, well, now, pause just momentarily. I illustrate with some example here. Here I'm picking z1, z2, I divide. So what the step would be, you have the fraction, then you multiply the whole thing by the complex conjugate of this number, which we said you just negate here. So you'll have this is what you have times complex conjugate of this divided by the same number. Then you expand the usual way. Anyway, we'll come to that, but that's basically what's happening here. So that later on, don't be wondering, okay, so how did this end up? Okay, so here you're just using z1, which is x1 plus iy1, which is this, divided by x2 plus iy2. Then now you do that thing of this, this divided by this, you multiply by the complex conjugate of this, which is x minus iy2 divided by x minus yy2. Then you expand the usual way we've expanded. You will end up with this. Then the last three, which I just say in commutative law, just talks about order for any two, whether you are adding or multiplying, doesn't matter. It's called commutative law. And lastly, when you have any three complex numbers, z1, z2, z3, then order for them, whether you're adding or multiplying, it doesn't change. It's called associative law. And lastly, you're talking about distributive law. And distributive law just says that you distribute Z1 over Z2 plus Z3, and then you have Z2 times Z1 times Z2 plus Z1 times Z3. That's called distributive law. All these are satisfied by R, real numbers, rational numbers, and those integers modulo P, where P is a prime. Okay, example. Given two complex numbers, Z1 equals 2 plus 4i, and Z2 equals minus 3 plus 8i, find the sum of the two and the product of the two. Well, the sum we just said, you just take 2 plus minus 3 gives you minus 1, and 4i plus 8i gives you 12i. Khalas, we finish. Then Z1 plus Z2, or rather, multiplication of the two numbers, you just expand. 2 times minus 3 is minus 6. 2 times 8i is 16i. Minus 4i times 3 is minus 12i. And then 4i times 8i is 32i squared. But i squared is minus 1, so this just becomes minus 32. And then you just take the real and the imaginary together. This is real, so it's minus 38. And this imaginary is 4i. Finish. Well, we're almost done, but not yet. Then the second last definition is what you call conjugate. We already saw conjugate anyway. So we just say that any complex number with x expressed in the form of x plus iy, its complex conjugate denoted by z is x minus iy. And it satisfies the following properties. By this, you can prove all of them. You should actually prove them now that you have a lot of time at home. What else are you doing as we learn remotely? But I'll illustrate for you. For instance, the first case here. This means the conjugate of the sum of Z1 and Z2. And this should be equal to the individual conjugates sum. Now, I can prove that for you by talking. Since it's a video, you can always go back and check. So, if Z1 is this and Z2 is this, we want to prove that property. So, if you take Z1 plus Z2, you get this number, a complex number. What's the complex conjugate of this? It's x plus x1 plus x2 minus I y1 y2. So this is this part. Now this side, what do? We take complex conjugate, individual, and add. So the complex conjugate of this is x minus I y1. And the complex conjugate of this will be x2 minus I y2. We add the two, what do we get? x1 plus x2 minus iy1 minus iy2, which you can put in brackets. So you end up with something that, with x1 plus x, with this one, but now with this part negative. So that proves equality of this property. The same thing you'll do for subtraction. Multiplication is similar, actually, ladies and gentlemen. You can also prove it. Now, where do you have multiplication? Oops, I'm going the wrong direction, I'm sorry. Now, multiplication, you had these numbers. You see, when you multiply this one by this, you end up with this. What's the complex conjugate of this? It's just this minus this plus that. Now, to prove the other side, you will take the complex conjugate of Z1, which will be x1 minus iy1. You multiply by x2 minus iy2. You will get the same thing. That's how I mean when I say you prove. Okay? This one, similar. This one and this one, I'm just giving you definition which you can prove. So the real part of z is x. We already saw that. Z is this, so the real part is x. And this is given by z plus the complex conjugate of z divided by 2. How to prove that? Well, very easy. This plus this, you can see this cancel out. You end up with 2x on this side. And then to this side you have z plus by z. If you divide by 2, you end up with x equals z plus by z over 2. Finish. The last one, how do you prove? You subtract. And when you subtract, you end up with the real part is z minus by z over 2. There should be I actually there. Okay, ladies and gentlemen, example which I was already showing you, but then let's look at it quickly. Given that z1 is 2 minus 3i and z2 is 4 plus 6i. Well, find z1 over z2 and 1 over z1. So how do you go about this? Well, the same process I already explained to you. What did I explain to you? That, let me change position so I don't get very much. So z1 over z2, this is a complex number you're dividing. So what do? You multiply by the complex conjugate of this, which is 4 minus 6i, and then you divide by the same number. Expansion gives you 2 times 4 is 8. 2 times minus 6i is minus 12i. 3i times 4 is minus 12i plus 18i squared. So this here becomes minus. You subtract and then you get the same expansion. So this is what you end up with, which you can write in. You split the real part and the imaginary part. The real part is minus 5 over 26. The imaginary part is minus 6 over 26. Okay? Then for this last part, 1 over z1, you just multiply by the complex conjugate of this, which is 2 plus 3i divided by 2 plus 3i, which ends up giving you 2 plus 3i over 13. Well, 13 comes from 2 times 2 minus, plus 6i minus 6i plus 9, or rather minus 9i squared, which becomes 9. So 4 plus 9 is 13. So the real part, the imaginary part. Finish. Okay, maybe we are done now. We just have the last one. So the last two definitions, or one definition is absolute or modulus value of a complex number z, denoted by that, is given by, you just square the real part, the imaginary part, find the square root. And this turns out to be the square root of z times the complex conjugate of z. Please check this part. Then there's a proposition which you may have seen in section 1.8, which just says that for any two complex numbers, z1 and z2, we take the modulus is less or equal to the modulus of the individual modulus of the two numbers. This you can check also. You can prove actually, because section 1.8 we are dealing with proofs. So the last example just says that if z is this complex number, determine the modulus of z. So this will just be 2 squared plus minus 3 squared, square root, which is 13. Ladies and gentlemen, I believe that's it. I don't know whether you have any questions. Maybe you will forward them to me, to the system. Have a nice evening or whatever time you watch the video.